Okay, so in this lecture note number 13, we are gonna study the matter semiconductor context as practical ohmic context in integrated circuit chip, and lastly but not least, not not DC characteristics, but AC characteristics of MS contact is going to be introduced. Afterwards, if time is allowed, we are going to start the introduction to PN junction diode. Okay, so what the practical ohmic contact? What is it? As I told you, in practice, most of the MS contacts are rectifying. In other words, if you didn't, finely tune the features and characteristics of MS contacts, its function of MS contact is rectification. So in practice and in integrated circuit chip, a certain some engineering solution is necessary to make the MS context of physical behavior being ohmic. So what is the cost-effective solution to have the MS contact with ohmic feature? So on the bottom side, you can see the engineering solution. In order to achieve a MS contact which conducts easily in both directions, yes, the answer can be found there. We can dope the semiconductor very heavily. So in MS diode, if the semiconductor part is very heavily doped, uh, we can make sure that this MS contact being to be ohmic contact. So what is the main physics behind it? If we draw the energy band diagram along the x direction, we're gonna get this energy band diagram. So I'd like to indicate the very narrow depletion width. Okay, so as we have, you remember the equation for the depletion layer width in MS diode, right? And it is proportional to the 1 over root n sub D or A, right? So if you increase the doping concentration as much as possible, the depletion width would become, even narrower than 10 nanometers. So if the depletion width is narrower than 10 nanometers, the electrons in conduction band in semiconductor part and the electrons in matter side can move in both direction. Back and forth, the electron can freely moves. Why? Even though there exists an energy height. From the perspective of electrons in conduction band in semiconductors, still there exists a energy barrier height. And from the perspective of electrons in matter side, still there exists Schottky barrier height. So as we have learned, this electron in matter side should be excited to overcome the Schottky barrier height, then it can freely move into the semiconductor side. What about the electrons in semiconductor? As we have learned, it should be excited up to the energy level at which it can freely move toward the matter side. But if this narrow width has been formed, in other words, the depletion layer width of MS contact is narrower than 10 nanometers, the electrons near the interface between matter and semiconductor can move without any energy barrier height, but can move uh, into semiconductor side or into matter side. What is the physical origin of this movement? Previously, we assumed that the electron is, solid, rigid, kind of ball uh, as a particle. However, if this elect but because of the duality of particle or small nanoscale particle, it it is like a wave. So uh, if we focus on the wavy, the feature of wave of electron, then this electron's wavelengths can affect and exist on the matter side as well. And if there is electrons wave, and this part of or tail portion of the wave of the electron in matter side can also simultaneously exist in semiconductor side. So uh, if whether or not the part of or tail part of the wave of electron in matter or semiconductor exists in opposite side is very dependent of the depletion layer width. As long as depletion layer width is below 10 nanometers, then the wave-like feature of electrons can affect and can explain physically how come the electrons can move back and forth in between matter and semiconductor. Okay, so this physical event can be described as the word of tunneling. Okay, so as described here, the depletion layer with W is so narrow that carriers in MS diode can tunnel, MS contact can tunnel directly through the barrier. Okay, so as long as the depletion layer width is very narrow, the carriers can never doesn't need to be excited up to overcome the energy barrier height. If once the depletion layer width is very narrow, such as 10 nanometers or narrower, then carriers such as electrons and holes in M and S part can directly tunnel through the energy barrier height, the energy barrier. Okay, so this tunneling mechanism can be used to physically explain how come the MS context can become ohmic-like when the semiconductor side is very heavily doped. Okay, and this idea can be used to have and to fabricate the MS context to be ohmic context. So the simple engineering solution is please dope your semiconductor very heavily or very degeneratedly. Then you can get a ohmic contact feature in your MS contact. So what is the main applications of this ohmic contact? I guess, yeah, let me write down here. You know the MOSFET. In undergraduate class, you have a chance to learn the MOSFET. So just remember how look it is. Okay. So this is a very simple MOSFET in a P-type substrate. So this is M plus source and drain, and that is gate oxide layer, and gate poly. So usually polysilicon has been widely used, at least in 45 nanometer technology node and beyond. The titanium nitride has been deposited right onto the gate oxide layer, and even the gate oxide layer has been replaced with a hafnium dioxide, you know, to claim it as a high K material. So some more advanced, things will be studied in the lecture to be offered next semester. But in this semester, we're gonna stick on the some fundamental and basic things. Okay, so here whenever we are saying that this three-terminal MOSFET, some textbook has introduced that we can use and take advantage of using a fourth terminal named as body. So body. So body indicates that this is a P substrate. Then my question is how to deliver your body signal, body voltage to this MOSFET. Can you deposit the metal side on the back side of substrate? No, this is not allowed. Then you should deposit a metal material onto the P side. Then this semiconductor P side, okay, MS contact should be ohmic like. Otherwise, you are going to make a diode here. But this is parasitic one and the thing that we didn't want to have it. So this MS contact should be very ohmic contact like. Okay, for that purpose, this semiconductor part right below the matter should be very heavily doped. So once the matter, usually contact pillar type contact has been formed, and right below this part should be very heavily doped. Then your body biasing has been applied and delivered throughout this pillar type contact. Afterwards, this P++ region can become, can can be working as, you know, as a driving force, or how to say, just the main driver to have the MS contact to be ohmic like. Okay, so that once your body bias has been delivered throughout this MS ohmic contact, then you can modify the threshold voltage of this MOSFET, by adjusting the body biasing, threshold voltage of MOSFET can be modified. So this is the real situation, how the body biasing can be delivered to your transistor. So in this MS contact, uh, its current voltage characteristic should be ohmic. Okay. All right. So on the top side, you can see that the energy band diagram along the x direction of a MS contact, SS, MS, SN++ heavily doped semiconductor has been drawn. So now electrons in metal side, electrons in semiconductor side can move back and forth. Okay. And some more details of how the tunneling has been occurred across the MS contact, but I guess I don't want to go in details. But just for your information, tunneling probability P has been denoted and described as a function of a Shockley height and VA applied voltage and doping concentration. And notice that there is H. H is named as Hamiltonian, and this Hamiltonian is closely associated with effective mass and effective mass. So the higher or the heavier the effective mass is, the higher the Hamiltonian is, and it would negatively affect the tunneling probability. Okay, and on the last line, you can see that the current density from semiconductor to matter is defined as unit charge times a whole donor's concentration. In other words, electron concentration times thermal velocity along the x direction, VTHX, and one more additional term, that is, P. P is tunneling probability. So in the last movie clip, we have learned that the current density is proportional to the unit charge carrier's concentration times velocity. But in this case, one more additional term has been included in deriving the current density from semiconductor to matter. That is tunneling probability. So other than tunneling probability, everything is very similar. Okay. Okay, so now let's slightly switch gear and try to understand a specific contact resistivity denoted as rho sub C. So the unit to indicate the specific contact resistivity is ohm times square centimeter, not ohm divided by square centimeter, ohm times square centimeter. That is the unit for specific contact resistivity. So what is the definition of the rho sub C, specific contact resistivity? Yes, as described on the second bullet, you can see that the rho C is the resistance of, not resistivity, resistance, okay, resistance of 1 square centimeter contact. So if I draw the cross-sectional view of matter and p-type substrate, so some thin film of matter has been deposited onto the p-type substrate, and if I draw it three-dimensionally, you can see this and say that this area is 1 square centimeter. Then uh, this interface, uh, the area of interface is the 1 square centimeter. Then what is the contact resistance value of this 1 square centimeter contact? Yes, that is rho sub C. So rho sub C is ohm times square centimeter. Okay. Let me see. For a practical ohmic contact, I mean, in as the preferred ohmic contact in integrated circuit chip, device engineer wants smaller Schottky barrier height and a higher or heavily doped doping concentration for to implement small contact resistance. As, as desired, the smaller the specific contact resistivity is, the better it is. Why is that? Because MS contact itself, uh, becomes and work as a kind of barrier uh, when it comes to flowing current in integrated circuit chip. So the smaller, the better when it comes to the specific contact resistivity. So herein, please remember the definition of a specific contact resistivity, which has been widely used in industry. So if you have a job in industry, you maybe have a tons of chance to use a specific contact resistivity in designing chips, in coming up with your own process recipe to build up a small, very small, super small specific contacts. Okay. All right. This idea, how to make Schottky barrier height lower and lower, has not been introduced and described in your textbook. But these three main engineering solutions are obtained and from top-notch conference papers. So this is only for your information, but if your research topic is associated with the MS contact, then please keep an eye on those three major approaches, how to lower the Schottky barrier height. Okay, or maybe in the near future, if you have a job in industry, your boss would ask you to look for the approaches to lower Schottky barrier height in MS contact, and please remember those are three main approaches and new main ways uh, to lowering Schottky barrier height. So the very first one way is we can take advantage of using immediate force barrier lowering. So what it is, as described, as derived, as drawn on the left hand side, when MSN plus plus contact, if you draw the energy band diagram, you're gonna see this sharp uh, black colored one. But in rear, because of this image force, the energy barrier height or top portion of the energy barrier has been lowered because of this image force. Okay, so the basic idea of image force is once an electron is existing near to the interface between matter and semiconductor, the electrons in matter side can also be pushed away because of the force coming from the electrons. But it looks like a kind of not real force, but it's a not real means an imaginary or image force. Okay, so the researchers have studied how much Schottky barrier lowering can be happened because of this image force, and it turned out that the delta phi the energy barrier height lowering can be described with this equation, and it is associated with the doping concentration in surface area, and A indicates the width of heavily doped surface area, the depletion width as we outlined. Okay, and the second approach is to lowering shock barrier height is work function engineering. So by modifying the work function of matter side, we can uh, modulate the shock barrier height. So one of the specific ways of matter work function engineering is we can use impurity segregation throughout the silicidation. As I told you, to reduce the to reduce the resistivity between matter and semiconductor, we're going to induce a chemical reaction between matter and semiconductor, then resulting in a silicated layer, such as titanium nitride, no, nickel silicide. So we can say in NISI silicidation layer. So using this silicidation layer, we can segregate the impurity dopant atoms away from the MS interface. Then we can modify the work function value of matter side. And the second way of doing work function engineering is to use a dual silicide technology. So low pi m and high pi m. So using a very, two separated values of work function, we can tune the work function of matter side. The third approach is to lowering shock barrier height you know, has been implemented using a bandgap reduction. So, silicon material is a mainstream, and its bandgap is 1.12 electron volt. However, if we can do some magics to tune the silicon to silicon at atomic distance, such by, for example, the stress engineering, or you know, by doping the silicon atom with uh, dopant atoms such as germanium, then the silicon material's unique original bandgap energy could be tuned. Okay, so stress engineering or germanium incorporation, those are the good options when it comes to modifying and reducing the bandgap energy of silicon. So most of these engineering solutions has been well explained in the conference papers. So please take a look at it if you're interested in it. Okay, so before moving on to the AC part, I guess this is the last one regarding the DC characteristic of MS contact. So as described in this lecture note, ideally, contact resistance is very small. That's true, not very high. So very little voltage is dropped across the ohmic contact. So in that sense, applied voltage is quite almost zero. So equilibrium conditions prevail across the ohmic contact. Okay, so this idea can be used uh, when you apply, high voltage across MS contact, but still the the resistance value across the MS contact is super small. So whatever the voltage is applied across the MS contact, we can reasonably assume that the voltage drop across ohmic contact is almost zero. So we can consider the biased MS contact as MS contact at thermal equilibrium. Okay, so everything comes from the fact that the resistance value across the ohmic contact is super small. Then we can ignore the voltage drop when the current is flow throughout the MS contact. So this is quite straightforward, and I guess that's very easy to understand the basic concept. All right, that's all for the DC characteristic of ohmic contact and MS diode. And in the next slide, I guess I need to explain some more capacitance versus voltage characteristic of MS diode. So I guess it's a good time to have a short break time, and see you in the next movie clip. Bye bye.